I'm Sam Guiterrez from the Programming Models team in the Applied Computer Science group at Los Alamos National Laboratory. And I will be talking about some of our work investigating data-centric models for multi-level algorithms. Okay, so some motivation. There are a lot of really neat and interesting toys out now, and more that are on their way. And the coolness factor is definitely subjective and depends on whether or not you have to get your codes up and running on this eclectic set of toys, right? But we can probably all agree that we are definitely living in interesting times. DOE has noticed, and they say it's time to level up. According to a recent DOE Oscar report, DOE scientific communities now face a crisis in extreme scale scientific software productivity due to a powerful confluence of factors, ongoing disruptive changes in computer architectures, and new frontiers in modeling, simulation, and analysis of complex multi-scale and multi-physics phenomena. So the question is, how are we going to productively program emerging HPC architectures in the face of increased heterogeneity at many subsystem levels? So the next big supercomputer at LANL, Trinity, for example, is going to have internode level heterogeneity, Haswell's on half the cluster and KNL's on the other. Intranode level heterogeneity, so things like Ornell's Summit, that's going to be power plus NVIDIA. And we're already seeing asymmetric network performance characteristics on Crane's Gemini and Aries networks, heterogeneous memories like high bandwidth, low bandwidth memory on Intel's KNL architecture. And if this wasn't sort of enough, we now have to deal with work on scheduling and load balancing on potentially noisier systems and a whole bunch of other hard stuff that I'm probably not qualified to talk about. And researchers like individuals in my team and some of our collaborators, for example, are already investigating several interesting paths, some of which have to do with embedded DSLs, that is, domain-specific languages that are hosted in a general purpose language, like C, for example. And in particular, these sorts of languages that leverage powerful task-based runtimes to run on heterogeneous distributed memory machines. Sort of one of the reasons that exploring the design space in eDSLs right now is a little friendlier has a lot to do with the emergence of things like LLVM and Clang, right? Basically, we don't have to write a compiler from scratch anymore, which is convenient. And this particular talk is actually going to focus on a particular task-based runtime that my team is interested in, called the Legion. And sort of before getting into our work with Legion, let me acknowledge the larger team from Stanford, NVIDIA, and LANL. These guys have done a lot of really good work. Okay, so what is Legion? Legion is an open source, data-centric, parallel programming model and supported runtime. It's written in C++, and it implements sort of all the machinery required to run Legion applications on parallel and distributed, in a parallel and distributed manner across HPC resources, that is, shared memory machines. A Legion port of S3D is already sort of running on 8K nodes on Titan and on both CPUs and GPUs. That is, a Legion version of the code is running faster than the fastest sort of accelerated MPI plus X version currently available, so it's promising. Okay, so basically at a high level, Legion can be thought of as a fine-grained, imperative, coarse-grained functional model with sequential semantics that dynamically extracts both task and data parallelism from Legion applications. So a little background here, let us recall that the imperative programming model describes computation in terms of statements that change program state. So in this model, sequences of commands are defined, and those are what the computer sort of executes. And the functional model is different in that it focuses on what the program should accomplish without necessarily prescribing the sequence of actions to accomplish the task. So, and I'm not like sort of talking about Haskell or anything here. Pure functions can actually be expressed imperatively, things like ls, grep, and sort. So, okay. So a bit of a warning here. I'm going to gloss over some of the details about Legion in the interest of brevity. So please take this moment and stop paying attention to me right now and check out some of the videos and papers and slides here at this link. Plus, I always sort of mess up the details of the runtime. So reading, you know, if you're interested, reading the papers is definitely in your best interest. So for the purposes of this talk, you'll need to know 3 things about the core Legion model. Legion is organized around an abstract collection called logical regions, which can be recursively partitioned, and units of parallel execution called tasks, which operate on these regions. Logical regions name a set of objects. They have no implied physical layout and have no implied location in the machine. Tasks are functions that operate on regions, and they are functions with controlled side effects that the runtime can reason about. So logical regions provide a way for you, the developer, to sort of describe your data to the runtime. This is where sort of the data-centric part of the title comes from. So conceptually, structured logical regions can be thought of as n-dimensional arrays of structs. So if I want an array of 4 of these things, conceptually I want one of these things. So I describe it to Legion like this. I describe it to Legion in terms of logical regions, which are the Cartesian product of an index space and a field space. And please note that that at runtime, one can actually request a particular physical layout of the data. So for example, AOS, SOA, hybrid. And this ability sort of hints to another sort of Legion capability, which is actually kind of a nice design decision. Legion applications are split into 2 pieces, sort of the functional piece of your code, which implements your algorithms, and a mapper that sort of implements and describes how data are laid out and sized and how tasks are scheduled. And another nice thing is a poorly implemented mapper in Legion cannot actually affect the correctness of your code. It'll definitely impact the performance of your code, but now you sort of have a path forward for portable performance without actually touching the core functional piece of your code, which is kind of nice. Okay, so now I actually want to operate on these data in a data parallel fashion. So now what? I first color the index spaces, and I split them into n pieces. And conceptually, we already are sort of familiar with this because we already do this in MPI land when we apply a domain decomposition scheme. So these pieces may or may not be disjoint. That is, they are non-overlapping. In this particular example, as you can see, they are disjoint. Then I enqueue a set of Legion tasks that will operate on these data in a data and potentially task parallel fashion. Note, task parallelism in Legion is implicit. That is, you don't have to worry about extracting this type of parallelism from Legion applications, and I will talk about why this is true later on in the talk. Also notice that I said enqueue a set of Legion tasks. In Legion, you never explicitly call functions. They are called by the runtime. So this allows the runtime the ability to potentially relax strict execution ordering of tasks if it is able. Okay, so now more on what Legion calls coloring. In this particular example, we can see that data can be colored in a variety of ways. represented by the respective colors. We do this to describe shared data that span domains, so sort of this sort of thing, and private data that can be potentially operated on in parallel and require no cross-domain communication. You can also maintain various colorings of logically the same data, so you could actually apply different coloring schemes to the data, and this has some nice properties that I won't get into right now. Okay, so now I actually think we have enough background to actually start talking about some of our porting work to Legion. So we ported a couple of MPI applications to Legion last year, an unstructured mesh Hydro mini app called Pennant, and HPCG, an MG preconditioned CG code. Setup constructs a sparse linear system. It has 27-point stencil at each point in the 3D domain. And the equations at IJK depend on its 26 neighbors. The global domain is defined to be this thing here. The local subgrid dimensions are nx by ny by nz. It solves ax equals b via mg preconditioned CG. And where A is a sparse matrix, B is known, and X is computed. So this is one of our vehicles for investigating some of these models. LGNCG implements all of the kernels found in the reference MPI implementation. It is a complete rewrite using only Legion, and we are using it as a vehicle to sort of investigate a bunch of things like abstractions, performance trade-offs, resiliency. The code is currently on GitHub, so you can check it out if you are interested. And I am happy to answer any questions. You can sort of hit me up on GitHub or email if you like. The building blocks of the code are pretty standard and what you would probably expect. We need a way of describing distributed vectors and sparse matrices to the runtime. And we do this by defining vectors to be structured 1D regions, and for sparse matrices, we simply take several vectors and construct ELL sparse matrices. We also need a partitioning scheme. Luckily, most of the kernels found in this benchmark code can easily be partitioned using a simple block 1D decomposition scheme, and some conventions used for the remainder of the talk. Colors here represent disjoint subregions, partitioning of the data. Okay, so let's take a look at two simple examples on how we would represent these operations using Legion's data-centric model. So first, we describe the data structures to the runtime. For this scaled sum, we describe 3 arrays basically. And then we apply the same disjoint coloring to all 3 since there are no cross-domain data dependencies. And then we tell the runtime how we are operating on the respective arrays with 2 annotations. So the first, permissions, and those state a task's data access requirements, and that's represented by these sort of black annotations here. For example, read only or write discard, or more commonly, just write only. And coherence. Coherence sort of states the required semantics of concurrent region access. And for this example, since these things are all disjoint, exclusive access is sufficient. And similarly, we can sort of see how we would describe a simple dot product here in Legion. And in the Legion model, Legion rewards precision. Over specificity will result in poor performance, and under specificity may result in runtime errors and or poor performance. I'll show an example of what I mean by that. So if we take a look at a naive sparse matrix vector multiplication implementation, if we don't apply a coloring to X and we just sort of say we don't know what actually talked about this yesterday. HPGM-GFV is an implementation in C, and it uses MPI with an OpenMP option. It proxies FV-based geometric MG linear solvers found in some AMG codes, for example. And the important bit about it, at least for our purposes, is that it implements a more complicated set of kernels, therefore requiring more expressiveness from our higher level abstractions that we are building on top of Legion. So in that regard, it's very useful to us. For this port, we are also exploring a slightly different execution model that is atypical for a Legion application. What we do is we effectively, this effectively amounts to a very early SPMD style model, which is represented at level 1 here. And we get there by basically defining a disjoint region of ints and partitioning it up so that we get this parallel launch very early on, and then within each task, they are responsible for managing their own logical regions, and then they use Legion's SPMD capabilities at this level to sort of communicate, and then at levels strictly greater than 1, our plan is to use a pure Legion model. And sort of based on my chatting with sort of several application developers, this SPMD style is well understood in the community, and our hope is that it may be useful in easing the move to this model or a similar model. But there are some open questions in going with this approach. So what are the implications of this hybrid model? That is, are there performance and or resilience implications? And is this approach reasonable for moving existing codes to this model? And hopefully sometime in the near future we'll have more answers and questions, so stay tuned. Thanks. Any questions? I'm gonna go here, get a shot of that, and then some performance stuff if you're interested. But
okay. Let's thank them.